There is a spacecraft flying through the inner solar system right now that almost nobody in the Western world is talking about. It was launched by China. It is called Tianwen-2, and it is on its way to do something that has never been attempted before in the history of space exploration. But before it reaches its final destination, it is going to stop off at one of the strangest little objects in the entire solar system. A weird, spinning, shape-shifting rock that orbits the sun in a way that defies easy explanation. A tiny world that sits right at the boundary between asteroid and comet, blurring the lines between two categories that scientists spent decades thinking were completely separate things. And what Tianwen-2 is going to find there, what it is already beginning to reveal just by the nature of the mission itself, is something that the Western press has almost completely ignored. If you follow space news through English-language sources, you probably have not heard this story in any real depth. And that is a genuine shame, because what is happening here is one of the most scientifically important missions of the decade. So if you are the kind of person who wants to understand what is actually happening out there in the solar system, and not just the missions that get the big press releases and the Hollywood documentaries, then stick with me. And if you find this kind of deep dive useful, hit subscribe right now, because we do this regularly and you will not want to miss what is coming next. Let us start from the beginning. The object at the center of this story is called 311P. Pan-STARRS. That name alone tells you something. The 311P designation means it is classified as a periodic comet, meaning it has a known, predictable orbit that brings it back around the sun on a regular schedule. Pan-STARRS refers to the telescope system that discovered it, the Panoramic Survey Telescope and Rapid Response System in Hawaii, and it was discovered in 2013, which in the grand timeline of astronomy is extremely recent. We are not talking about some legendary comet that ancient civilizations watched streak across the sky. This is a newly discovered, poorly understood, deeply strange object that we have only been studying for about a decade. When astronomers first spotted it, they thought it was unremarkable, just another small body tumbling through space in the inner solar system. But then they looked more carefully, and what they saw made them stop and look again, because 311P does not look like anything else we have ever seen. It has tails, multiple tails, not one, not two, but somewhere between 6 and 9 distinct dust tails extending outward from its central body at the same time. If you look at the Hubble Space Telescope images taken of 311P back in 2013 and 2014, the thing looks almost like a spinning pinwheel, or like a child's drawing of the sun, with rays shooting out in all directions. It is bizarre. It is visually unlike almost anything else in the known solar system, and explaining why it looks that way turned into one of the more interesting puzzles in planetary science. Here is the thing about comets. Normally when we talk about comets having tails, we mean a single tail. Sometimes two. There is the dust tail, which reflects sunlight and appears white or slightly yellowish, and there is the ion tail, which is made of charged particles being pushed directly away from the sun by the solar wind, and it appears slightly bluish. These two tails always point roughly away from the sun, which is why if you photograph a comet over several nights, its tails appear to sweep and shift direction as the comet moves through its orbit. That is normal. That is what a comet is supposed to look like. 311P does not do that. 311P has multiple tails arranged around it at different angles simultaneously, not shifting in response to the solar wind in the normal way. These are dust tails, yes, but they have been produced at different times and in different directions, and they are still visible all at once because the dust in each individual tail has not yet dispersed. What you are seeing is the record of multiple separate ejection events, all frozen in space around this tiny object, like a history of its recent behavior written in dust. The leading theory for why this happens is something called the Yorp effect. Yorp stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, which is a remarkable number of scientists to name an effect after, but here we are. The Yorp effect is the process by which solar radiation, specifically the absorption and re-emission of sunlight, can gradually change the rotation rate of a small body over time. When sunlight hits one side of an asteroid or comet, it heats up, and then that surface re-radiates that heat as infrared radiation, and that re-radiation produces a tiny but real force. Over millions of years, this can spin a small object up faster and faster, and if it spins fast enough, material starts to fly off the surface due to centrifugal force. Not in one catastrophic explosion, but gradually, in pulses, as the surface reaches its breaking point in different places at different times. Each ejection event sends a stream of dust and small particles out into space, and each of those streams becomes a separate tail. And because the object is continuously spinning as it ejects material, the tails come out at different angles, which is exactly what we see when we look at 311P. So at first glance, it looks like a comet with multiple tails, but it is not really behaving like a comet at all. Comets, in the classical sense, are icy bodies. When they get close to the sun, the ice sublimates, meaning it turns directly from solid to gas without passing through the liquid phase, and that outgassing drags dust particles with it, creating the coma and the tail that we associate with a comet. 311P does not appear to have significant ice doing that. The ejections that create its tails seem to be driven primarily by rotation and the Yorp effect, which is more like what happens with asteroids. Specifically, a class of objects called active asteroids. Active asteroids are one of the more recently recognized categories in solar system science. They are objects that orbit in the asteroid belt or in asteroid-like orbits, but they display comet-like activity, meaning they have tails or comae, but for reasons that are not driven by ice sublimation in the traditional comet sense. Some of them eject material due to impacts, some due to the Yorp spin-up effect, some due to thermal fracturing, some due to ice that is buried deep enough that it only sublimates very slowly. The boundaries between asteroid and comet, which used to seem very clear and well-defined, have turned out to be much blurrier than anyone expected, and 311P sits right in that blurry zone. The official classification of 311P as a periodic comet is essentially a legacy decision. It was put in the comet category because it displayed comet-like activity when first discovered, but the scientific community largely considers it to be what is called a main belt comet, or more specifically, an active asteroid. It orbits in the inner solar system, not in the far outer reaches where classical comets originate. Its orbit is not the kind of wildly elongated ellipse that you expect from a comet that formed in the Kuiper belt or the Oort cloud. It behaves, in many ways, like an asteroid that is doing something unusual. And that is precisely what makes it so valuable as a target for a mission. Because if you want to understand the boundary between asteroids and comets, if you want to understand what active asteroids are and where they come from, then you need to go visit one up close. You need to touch it, smell it, taste it, sample it, and bring some of it home. And that is what Tianwen-2 is being sent to do. Now, let us talk about the mission itself, because it is genuinely impressive in ways that have not been communicated clearly in Western coverage. Tianwen-2 is a mission designed and built by the China National Space Administration, known as CNSA. It was launched in May 2025. The primary goal of the mission is to visit a near-Earth asteroid called 2016 HO3, which was recently renamed Comet. This is a particularly fascinating object because it is a quasi-satellite of Earth, meaning it orbits the Sun in a path that keeps it in a stable, synchronized relationship with our planet. It is not a moon. The Earth does not gravitationally dominate it, but it dances around our planet in this intricate gravitational relationship that keeps it near us for centuries at a time. Scientists believe it might actually be a fragment of the moon, blasted off by an ancient impact, and eventually settled into this quasi-orbit. Understanding it could tell us something profound about Earth's history. But on its way to Comet, Tianwen-2 is making a flyby of 311P. This is the first ever dedicated close encounter with an active asteroid of this type. No spacecraft has ever done this before. The flyby is not a quick drive-by wave from a safe distance. The spacecraft is designed to get close enough to image the surface in high resolution, to analyze the dust environment around the object, to measure its composition using a suite of onboard instruments, and to do all of this in the kind of detail that only a spacecraft in the immediate vicinity can achieve. The instrument package on Tianwen-2 is worth going through in some detail, because each instrument is there for a reason that reflects a specific scientific question. There is a medium-resolution camera and a high-resolution camera, which together will build up a detailed visual map of the entire surface of 311P. When we look at 311P from Earth, even with Hubble, we see something that is only a handful of pixels across. We see the dust tails, we can infer the rough size and behavior of the object, but we cannot see the surface. We cannot see whether it has craters, whether it has ridges, whether it has areas of different color or texture that might indicate different compositions or ages. The cameras on Tianwen-2 will change that completely. There is also a thermal infrared imager, which maps the temperature distribution across the surface. This matters for several reasons. Temperature variations can tell you about the material properties of the surface, whether it is rocky, dusty, porous, or compact. They can reveal areas of unusual thermal behavior that might indicate subsurface structure. And crucially, for an active asteroid, they can help identify the areas where material ejection is most likely to occur, which connects directly to understanding the Yorp effect in action. There is a visible and near-infrared spectrometer, which analyzes the composition of the surface by measuring how it reflects light at different wavelengths. Different minerals, different ices, different organic compounds all have characteristic spectral signatures. By mapping these signatures across the surface, scientists can build up a picture of what 311P is actually made of. There is a laser altimeter, which measures the distance to the surface with extreme precision and builds up a three-dimensional topographic map. This allows scientists to understand the shape of the object in detail and to correlate features seen in the cameras with their actual dimensions. There are magnetometers and plasma analyzers to study the space environment around the object and understand how it interacts with the solar wind. There are dust detectors to directly sample and characterize the particles being shed by the active asteroid. And there is a radio science experiment that uses the Doppler shift of the spacecraft's radio signals to precisely measure the gravitational field of the object, which in turn reveals information about its internal mass distribution. This is not a casual flyby. This is a scientific assault on 311P using every tool available. And the data that comes back from this encounter will be the most detailed information we have ever collected about an active asteroid of this type. So why has this not been a bigger story in the Western press? The honest answer involves several overlapping factors that together produce a kind of systematic blind spot. The first factor is language. Chinese scientific papers, Chinese space agency press releases, Chinese mission updates are primarily published in Mandarin. The translation pipeline from Chinese scientific communication into English is slow and incomplete. By the time something gets translated and picked up by English-language science journalists, it may have been weeks or months since the original announcement. And if the English-language version of the story does not get picked up quickly, it often simply does not get covered at all. The second factor is institutional familiarity. Western science journalists and their audiences are deeply familiar with NASA, with ESA, with JAXA. They know the naming conventions. They know the press release formats. They have contacts within those organizations. They have years of context about the mission pipelines and the scientific communities. Chinese space missions lack that familiarity for most Western journalists. The names are harder to parse, the institutional structure is less familiar, the context is harder to build quickly. So stories about Chinese space science require more work and produce less immediate audience recognition, which in a media environment driven by clicks and engagement means they get deprioritized. The third factor is geopolitics. There is a tendency in Western media coverage of Chinese technology and science to frame everything through the lens of competition and national rivalry. Stories about Chinese space achievements often get filtered through questions of whether China is catching up with the United States, whether there is a new space race, whether Chinese satellites are a security concern. This framing is not entirely without merit, but it tends to crowd out the straightforward scientific story. When you start from the question of what does this mean for America, you often end up not telling the story of what this means for our understanding of the solar system. The fourth factor is simply timing. The Western space media landscape was, during the planning and early execution phase of Tianwen-2, largely consumed with other stories. The Artemis program, commercial crew developments, the James Webb Space Telescope, and its extraordinary output. Mars sample return planning. These are all legitimate, fascinating stories, but they filled the available bandwidth, and a Chinese mission to an obscure active asteroid did not have the immediate hook that breaks through a crowded news cycle. The result of all of this is that a mission of genuine scientific importance, one that will produce firsts and revelations and new understanding, has largely failed to register with the audience it deserves. And we should fix that, because the science here is extraordinary. Let us go deeper into what scientists actually hope to learn from 311P, because the implications extend far beyond understanding just this one small object. The question of where Earth's water came from is one of the oldest and most fundamental in planetary science. The early Earth formed from rocky, dry material in the inner solar system. The conditions during formation were hot enough that any water present in the raw materials would have largely vaporized and been pushed outward or lost to space. And yet the Earth is a water world. 70% of the surface is covered in ocean. There is water in the atmosphere, water in the crust, water in the deep mantle. Where did it all come from? The dominant hypothesis for decades was that it was delivered by comets. Comets from the outer solar system, icy and volatile rich, bombarded the early Earth during a period called the Late Heavy Bombardment, roughly 4 billion years ago, and the water they carried was incorporated into the planet. This is an elegant idea, and it has a lot going for it. But it has run into a significant problem. The problem is isotope ratios. Water is not just water. The hydrogen atoms in water molecules come in different varieties. Regular hydrogen, which has just one proton in its nucleus, and deuterium, which is a heavier isotope of hydrogen with one proton and one neutron. The ratio of deuterium to regular hydrogen in a sample of water is a kind of fingerprint that reflects the conditions under which that water formed. Water that formed in the cold outer solar system, where most comets originate, tends to have a different deuterium to hydrogen ratio than water that formed in the warmer inner solar system. When scientists measured the deuterium to hydrogen ratio in Earth's ocean water and compared it to measurements of cometary water, they found a significant mismatch. Comets from the Oort cloud, the classical comets with their spectacular tails and long orbital periods, have deuterium to hydrogen ratios roughly twice as high as Earth's oceans. If those comets delivered Earth's water, the deuterium enrichment does not match up. Something is off. Then attention turned to asteroids, specifically to a class of asteroids called carbonaceous chondrites, which are water-rich, carbon-bearing asteroids that formed in the outer asteroid belt. Their deuterium to hydrogen ratios are much closer to Earth's ocean water. This shifted the hypothesis away from comets and toward asteroids as the primary delivery mechanism. But here is where it gets complicated and interesting. The distinction between water-rich asteroids and comets is not as clean as it seemed. Active asteroids like 311P blur that boundary. They are in asteroid-like orbits, but they have comet-like activity. If they contain significant water ice, then they represent a population of objects that could have delivered water to the early Earth in ways that bridge the gap between the comet delivery hypothesis and the asteroid delivery hypothesis. Understanding the water content of 311P, understanding its isotopic composition if possible, understanding whether its activity is driven by ice or purely by mechanical processes, all of this feeds directly into the biggest question in Earth science. How did we get our water? And by extension, how did life get the medium it needed to begin? This is not a peripheral question. This is not a niche topic for specialists. This is as fundamental as science gets. And then there is the question of organics. Carbon-bearing compounds, the building blocks of biology. Carbonaceous asteroids and comets have long been known to contain organic molecules, not life itself, but the chemical precursors that could, under the right conditions, lead to the development of life. Amino acids, the building blocks of proteins, have been found in meteorites. Complex organic molecules have been detected in the gas clouds around forming stars. The universe, it turns out, is very good at making organic chemistry happen, even in environments that seem completely hostile to anything biological. If 311P contains organic compounds, and there is reason to think it might, given its orbit and composition class, then characterizing those compounds adds another data point to our understanding of how organic material was distributed through the early solar system, how it ended up on Earth. Whether the conditions that led to life here on this planet were unique, or whether they were the natural consequence of the delivery of raw materials that was happening everywhere, all at once, across the entire inner solar system. These are big questions. Tianwen-2 cannot answer all of them from a single flyby. But it can begin to narrow the field. It can rule out some possibilities and strengthen others. It can provide constraints that make future missions, including those that might actually land on or return samples from active asteroids, more targeted and more productive. Speaking of sample return, that is what Tianwen-2 does next. After its flyby of 311P, the mission continues to Comet 311P, the quasi-satellite of Earth, and there the plan is to collect a sample and return it to Earth. If successful, this would make China only the second country, after Japan, to have returned samples from two different small solar system bodies. Japan did it first with the Hayabusa missions to asteroids Itokawa and Ryugu. China did it with Chang'e 5 returning lunar samples. And if Tianwen-2 succeeds, they will have added a near-Earth asteroid to the list. The comparison to Japan's Hayabusa 2 mission is instructive. When Hayabusa 2 returned samples from Ryugu in 2020, the scientific output was enormous. Over 100 papers published within the first 2 years, new insights into the composition of carbonaceous asteroids, discovery of amino acids and other organic compounds in the samples, evidence of aqueous alteration, meaning the asteroid had once been in contact with liquid water, and those samples continue to be analyzed today, with new discoveries still emerging years after the return capsule touched down in the Australian outback. Comet 311P is expected to yield similarly transformative science, potentially amplified by the intriguing hypothesis that it is made of lunar material. If it turns out to be a fragment of the Moon, then its composition would be deeply familiar to scientists who have spent decades studying Apollo lunar samples. But if its composition does not match the Moon, that itself would be a major finding, ruling out the hypothesis and forcing a rethink of where these quasi-satellites come from and what they are made of. But all of that is Phase 2. Right now, in this moment, the first act of Tianwen-2's journey is its encounter with 311P. And this is the part that has been most completely absent from Western coverage. Let us think about what it actually means to be at 311P, to be close to it, to see it as a world rather than a point of light. 311P is tiny. Current estimates put its diameter at somewhere around 200 meters, though this is uncertain, and the high-resolution imaging from Tianwen-2 will significantly refine this number. 200 meters. That is smaller than the length of 2 football fields placed end to end. It is smaller than many buildings. If you were standing on its surface, you would be able to walk its entire circumference in a matter of minutes. At that size, the gravity is almost nothing. The escape velocity, meaning the speed you would need to throw something for it to escape the gravitational pull of the object and fly off into space, is probably somewhere in the range of a few centimeters per second. That is not a typo. Centimeters per second. If you picked up a rock and gently tossed it while standing on the surface of 311P, there is a real chance that rock would just keep going and never come back. It would become its own separate mini-asteroid, orbiting the Sun independently. The surface gravity is so weak that the concept of weight essentially loses all meaning. This has practical implications for the spacecraft, which is why missions to small bodies are so technically challenging. You cannot simply point your thrusters at the surface and land, because the moment you fire a thruster to slow your descent, you change your trajectory dramatically relative to the object. Small body operations require an entirely different approach to navigation and control than orbiting a large planet or even landing on the Moon. The spacecraft has to essentially match orbits with the object and then very, very carefully maneuver in its tiny gravitational environment. The Yorp spin-up effect that we discussed earlier is, on a body this small, quite rapid in geological terms. Over thousands to tens of thousands of years, the rotation rate of 311P has been increasing. As it spins faster, material on the equatorial bulge experiences stronger centrifugal force relative to the feeble gravity. Eventually, loose surface material begins to migrate toward the equator. Eventually, some of it gets ejected. This is the process that creates the multiple tails. What this means for the surface morphology, for what 311P actually looks like up close, is genuinely uncertain. There are no previous high-resolution images of an object at this stage of YORP spin-up. We have some idea from computer simulations. We might expect a somewhat elongated rubble pile structure. We might expect an equatorial ridge or bulge where material has migrated and accumulated. We might expect a relatively smooth equatorial region stripped of loose material that has been flung off, and a rougher, more textured polar region where gravity is slightly stronger relative to the centrifugal effect and material has been retained. But these are predictions. The reality might be quite different. And the reality, whatever it turns out to be, will be fascinating. Because 311P is a time capsule. It is showing us a process that must have happened to many other asteroids and comets throughout the history of the solar system. Objects that were once active in this way and then slowed down as they lost material. The surface of 311P is a record of this process in action, right now, in real time. Now let us talk about what the scientific community expects to learn specifically from the flyby observations, because there are some very targeted questions that the instruments aboard Tianwen-2 are designed to answer. The first question is the shape, not just the rough dimensions, but the detailed three-dimensional form of the object. Is it spherical, elongated, bilobed, like the Comet 311P/Churyumov-Gerasimenko, which famously looked like a rubber duck when the Rosetta spacecraft arrived at it? The shape encodes information about the history of the object. A bilobed shape suggests two separate objects that gently came together through a process called contact binary formation. A more rounded shape might suggest a rubble pile that has been reorganized by rotation. An elongated shape might reflect a history of mass loss from specific regions. The second question is surface composition. What materials are at the surface of 311P? Is there water ice exposed anywhere, or is all the ice buried beneath a layer of insulating regolith, the fine debris that accumulates on asteroid surfaces? Are there organic compounds, silicates, metal-bearing minerals? The spectrometer data will build up a map of composition across the surface that can be correlated with the visual features seen in the cameras. The third question is the dust environment. The dust detectors and the cameras together will characterize the particles being shed by 311P right now, during the encounter. How big are the particles? How fast are they moving? In what directions? This directly feeds into understanding the ejection mechanism and the YORP effect in action. The fourth question is the thermal behavior. The infrared imager will reveal how the surface temperature varies across the object and over time as it rotates. Hotspots might indicate unusual materials or structures. The overall thermal behavior constrains the thermal inertia of the surface, which is a measure of how quickly it heats up and cools down as it rotates. High thermal inertia suggests a rockier, denser surface. Low thermal inertia suggests a highly porous, dusty surface. This matters for understanding how the YORP effect operates in detail. The fifth question, and perhaps the most fundamental, is internal structure. The radio science experiment uses the perturbations in the spacecraft's trajectory caused by the gravity of 311P to map the mass distribution within the object. Combined with the shape model from the cameras and altimeter, this allows scientists to determine the bulk density of the object and to make inferences about whether it is a coherent solid body or a loosely bound rubble pile. For an object that is actively shedding material due to spin-up, the internal structure is critical. A monolithic solid body behaves differently under spin-up than a rubble pile does. Understanding which one 311P is helps explain why it is ejecting material in the pattern we see. Each of these questions connects to broader themes in planetary science. Each answer from 311P will be a data point in a larger picture that we are still assembling. The picture of how the solar system formed, how it evolved, how material moved around in the early chaotic period, how water and organics were delivered to the inner planets, how the boundary between rocky asteroids and icy comets got blurred, and what that means for the conditions that eventually gave rise to life. It is worth pausing on that last point for a moment, because it is easy to lose sight of the biggest thread running through all of this. When we look at an object like 311P, we are not just looking at a weird rock doing funny things in space. We are looking at a remnant of the conditions that prevailed in the solar system 4.5 billion years ago. The small bodies, the asteroids and comets, and everything in between are the leftovers from planet formation. The big objects, the planets, have been reshaped by billions of years of geological activity, volcanic resurfacing, plate tectonics, weathering, ocean chemistry, biological processes. Their original composition has been thoroughly mixed and transformed. The small bodies have not. They are old. Some of them are among the most ancient, least altered materials in the solar system. When we analyze an asteroid sample in the laboratory, we are sometimes looking at material that has not changed significantly since before the Earth existed. The chemical conditions, the mineral structures, the isotopic signatures, all of it is a record of conditions that are otherwise inaccessible to us. And within that record lies the story of how everything began, how the materials that eventually became you and me and every other living thing on this planet were processed and delivered and assembled. The carbon in your body was once floating in a molecular cloud in interstellar space. The water in your cells was once ice in the outer solar system. The phosphorus and nitrogen and iron that your biology depends on were forged in the hearts of stars that exploded before our solar system even existed. All of that material went through a chaotic, violent, incredibly productive period of assembly and delivery and collision and chemical transformation to end up here, organized into something that can think and wonder and ask questions about its own origins. Active asteroids like 311P are windows into that process, not the whole process. Not a complete picture, but a window, a small, irregularly shaped, actively spinning window that is currently ejecting dust tails in multiple directions and orbiting the sun in the inner solar system, waiting to be visited by a spacecraft that is already launched and is already on its way. The story is happening right now. This is not history. This is not a mission to a distant target decades in the future. Tianwen-2 is already in space. It is already traveling. The encounter with 311P is not some abstract future possibility. It is a scheduled event in the near term, and the data from that encounter will begin flowing back to Earth. And then scientists will get to work analyzing it, and papers will be written, and press conferences will be held, and at least within the Chinese scientific community, this will be treated as the major event it is. Whether the rest of the world pays attention is a choice. And the right choice, the scientifically honest choice, is to pay attention. Not because China is doing it, not for any geopolitical reason, but because the universe does not care about national boundaries. The physics of active asteroids is the same physics whether the spacecraft studying them was built in Beijing, or Houston, or Tokyo. The data is the data. The science is the science. And there is something else worth saying here. The global scientific community that studies small solar system bodies is genuinely international, in ways that sometimes get lost in the media coverage. Researchers in China, Japan, the United States, Europe, and many other countries collaborate on papers, share data, argue about interpretations at conferences, and collectively advance the field. The scientists who work on Tianwen-2 read the same journals as the scientists who worked on NASA's OSIRIS-REx mission to Bennu. They cite each other's work. They build on each other's discoveries. The nationalistic framing that dominates media coverage of space exploration is not an accurate reflection of how space science actually works at the research level. This is not naive idealism. It is just accurate. Science is a conversation, and every major mission contributes data that everyone benefits from. The Hayabusa 2 sample returned from Ryugu generated findings that researchers around the world are still working through. The Rosetta mission data from Comet 311P is still being analyzed and reanalyzed and mined for new insights. Whatever Tianwen-2 finds at 311P will enter that same global scientific conversation and contribute to understanding that belongs to everyone. Now, let us talk about the broader context of active asteroid science. Because 311P is not the only member of its class, and the mission to it is part of a larger emerging field. Until fairly recently, active asteroids were considered oddities, freaks, exceptions that somehow needed to be explained away rather than treated as a genuine population of objects with their own significance. The first active asteroid to be recognized as such was 133P/Elst Pizarro, discovered in 1996. It showed comet-like activity, but was clearly in an asteroid belt orbit. At first, scientists tried to explain it as a chance coincidence, perhaps a comet that had somehow been captured into an asteroid-like orbit. But as more examples accumulated, the idea of a genuine population of active asteroids became harder to dismiss. We now know of dozens of confirmed active asteroids, with new ones being discovered regularly as survey telescopes improve in sensitivity. They fall into several subcategories based on their suspected activity mechanism. There are the main belt comets, which appear to be activated by ice sublimation and tend to be repeatedly active near perihelion, which is the point in their orbit closest to the Sun. There are the rotational breakup objects like 311P, where Yorp spin-up is driving mass loss. There are the impact-activated objects, where a recent collision has exposed fresh material or generated a debris cloud. And there are some whose mechanism is still genuinely uncertain. Understanding these populations matters because they may represent a significant reservoir of water ice and organic material in the inner solar system. If main belt comets contain substantial ice, they represent a population of potential water deliverers that has been lurking in the asteroid belt throughout the history of the solar system. The asteroid belt is not as distant from the early Earth as the Oort cloud or the Kuiper belt. Delivering water from the asteroid belt to the early Earth is, in orbital mechanics terms, substantially easier than delivering it from the far outer solar system. This has implications for the Fermi paradox, that famous question of why, in a universe full of stars and planets, we have not detected signs of other civilizations. Part of the answer might lie in the specific conditions that allowed life to develop on Earth. If those conditions require a very particular configuration of the solar system, a specific architecture that delivers water and organics at the right time and in the right amounts, then habitable worlds might be genuinely rare. Active asteroids, and what they tell us about the delivery of life-sustaining materials, are directly relevant to understanding how rare or common the conditions for life might be. On the other hand, if water delivery was a robust and common process, if active asteroids in inner solar system orbits routinely delivered water to rocky planets in the habitable zones of sun-like stars, then the stage for life might be set quite widely across the galaxy. Either way, knowing which scenario is true is important, and every mission to an active asteroid like 311P is a step toward knowing. Let us now step back and look at the place of Tianwen-2 within China's overall deep space program, because this mission does not exist in isolation. It is part of a systematic expansion of capability that has been building for decades. China's planetary exploration program has been methodical in a way that reflects a long-term strategic approach to science. The Chang'e lunar program started with orbiters, moved to landers, progressed to rovers, and ultimately achieved sample return with Chang'e 5 in 2020, bringing back almost 2 kilograms of lunar material, the first new lunar samples returned to Earth since the Soviet Luna 24 mission in 1976. That is a remarkable achievement that deserved more sustained attention than it received in Western media. Then Tianwen-1 went to Mars in 2021. It included an orbiter, a lander, and a rover called Zhurong, all in a single mission. Delivering a rover to Mars is something only 3 entities have ever achieved: NASA, the Soviet Union, and now China. Zhurong operated on the surface of Mars and returned geological and atmospheric data. Again, the Western media covered the landing, but largely moved on before the scientific results began to accumulate. Tianwen-2, with its flyby of an active asteroid and sample return from a quasi-satellite, represents the next level of ambition. And beyond Tianwen-2, China has announced plans for Tianwen-3, which is intended to be a Mars sample return mission, and Tianwen-4, which targets Jupiter and its moons. These are not vague aspirational statements. These are funded programs with engineering teams working on them. The trajectory is clear. China is building a comprehensive deep space exploration capability, mission by mission, and the Tianwen series is the spine of that program. By the time Tianwen-4 arrives at Jupiter, assuming it launches on schedule in the early 2030s, China will have returned samples from 2 small solar system bodies, put multiple rovers on the Moon and Mars, flown by 2 distinct small body types, and be in the process of exploring the Jovian system. That is a program that matches or exceeds anything any single space agency has done in the same time frame. None of this requires the reader to have any particular political view. You do not need to admire or criticize any government to recognize that remarkable science is being done, that important data is being collected, and that the results of these missions belong in the broader conversation about our solar system. Tianwen-2 at 311P is the next chapter in that story. And it is happening whether we pay attention or not. The question is whether we choose to engage with the science or let it happen in a corner of the information landscape that most people never visit. The argument for engagement is simple. This is about where we came from, not where China came from, or America came from, or any particular civilization came from. Where we all came from. Where the water in our bodies came from. Where the carbon in our DNA came from. Where the conditions for life came from. 311P is a tiny piece of that puzzle, a 200-meter rock with multiple dust tails spinning in the inner solar system. But tiny pieces matter. The puzzle is too important to leave incomplete just because some of the pieces are being examined by spacecraft built in countries whose science programs do not get equal coverage in English-language media. There is also a lesson here about how we consume scientific information. The modern information landscape is deeply fragmented and unevenly distributed. Stories that do not fit the existing templates of what counts as a major space event often fail to register, even when they are scientifically significant. The Western space media landscape has default narratives. NASA missions good, SpaceX launches exciting, Mars interesting, asteroids unless they are threatening to hit Earth, not very interesting, China doing space things, covered primarily through a geopolitical lens rather than a scientific one. These default narratives are not malicious. They are just the product of how media organizations work, what their audiences are already interested in, what their reporters have backgrounds in, what stories are easy to tell quickly. But the universe does not organize itself according to default media narratives. Important things happen outside those templates all the time. And staying informed about science in the 21st century requires actively seeking out stories that do not automatically surface in the main feeds, the main channels, the main publications. That is what we are doing here. That is the point. There is a spacecraft in space right now, built by humans, on its way to a tiny, strange, actively spinning object that blurs the line between asteroid and comet, and in doing so, will help us understand something fundamental about how the solar system is put together and how the conditions for life were assembled. This is happening. It is real. It is scientifically important, and it deserves to be part of the conversation. When Tianwen-2 reaches 311P and the data begins to flow, the first images will be extraordinary. The object will go from being a blob of pixels, a smear of light with tails extending from it, to a world. A real, textured, detailed world with hills and craters and ridges and whatever else the surface turns out to hold. The scientific community will have their first look at a Yorp-spinning active asteroid in close-up detail, and what they see will either confirm their predictions or surprise them. In science, surprises are usually more interesting than confirmations. But even confirmations are valuable because they tell you that your models are working, that your physics is right, that you understand the process. And then the debate will begin. Papers will be published disagreeing with each other about the interpretation of the spectral data. Some scientists will argue that the activity is purely mechanical, driven by Yorp spin-up with no ice involvement. Others will argue that a small contribution from sublimating ice is necessary to explain some feature